All right. Good morning, everybody. Happy Monday. So, so I have the midterms graded. So I had it graded, I think, around Saturday night or so. So you should be able to view your midterm using Lockdown browser on Canvas. So, yeah, the average didn't really come out too well, so not really sure what happened there. But anyway, I guess I can cover a couple of questions here and there on the exam. I don't want to spend too much time going over everything because I do want to start going into hashing um, soon. And of course, if you have any questions on the exam as to why this was wrong or explanation for certain questions, of course, I can well, yeah, you haven't, I didn't actually really curve anything really on the exam. I just sort of, that was your grade right now. What I did is I just sort of made it where the midterm is worth only 15% of your grade and the final will be worth more. And the final exam should be straightforward because it's going to be several algorithms that we'll cover in class and you have to trace it out just like how I traced it out in class. So it won't be anything like surprising. So we'll go over a few graph theory problems during the semester here, and you have to trace that same algorithm on a graph. Nothing new really. Or there'll be another sorting algorithm we'll cover, and it's also going to be just just trace out as you did in class. So just like the homework assignment, I guess you could say. I guess you have to like kind of write it out. I mean, I guess there's two ways I can do this. So I guess what happened is you have to write out the arrays after every step. So for like Dijkstra's and Kruskal's algorithm, you have to sort of, show me step one, which node was selected, and then sort of write out the weighted paths array. So you don't have to write the whole array out, you just have to list them out like that. So you have to on paper sort of trace it out and sort of write the path weights after every step. So that actually does not give any students any real problems. From what I've experienced, they've always been able to very easily handle it on Canvas, so it should not be a problem. So usually the final exam does go a lot better because there's less tricks on there, yeah. So although I didn't make this exam really too tricky, but I guess maybe it was kind of overthought on certain situations, which might have been the reason why things didn't go too smoothly. So anyway, I'm going to go ahead and just sort of, I'm going to go ahead and talk about the exam a little bit here, but I won't cover every single question, but just some of them just to just give you an idea. But of course, you can ask me through Discord or office hours if you have any issues on certain questions. Like, of course, can go over what went wrong or why you missed it or whatnot. Let's go ahead and just begin a screen share into more detail. Put this over there. Alrighty. The midterms. So here's the complete test question bank. So let's look at these ones over here. So okay, let's look at this question. So f of n equals n root n minus n log n. So I've already proven in class that so n root n and n log n root n has a more dominant term because it's n times, they both have the same factor n, so we can sort of strip that away. Then we have root n and log of n. And I already showed you during the semester that root of n has a larger asymptotic growth rate than log of n. So this f of n function has a growth rate of n root n. That's the growth rate for f of n. Then g of n, we have n squared divided by root of n. So if you work out the algebra there, it's going to be n up to the 3/2, or n up to 1.5, or other words, n root n. So n root n, or n up to 1.5 is the same thing. So, and of course, plus n log n, well, again, the dominant term here is going to be n root n. So f of n, g of n have the same exact growth rate, which implies everything. Because if I say f of n and g of n are the same growth rate, then f of n equals theta of g of n is correct. But also, if I were to say f of n equals O of g of n, that's also correct. Because remember, so if f of n equals theta of g of n, that implies f of n is also O of g of n, f of n is also omega g of n. It implies all of that. So And I did have select all the valid statements. I just kind of like a key that there might be more than one answer. So a lot of people just selected one answer, I think, or that was might have been the issue, but it's all of them. Now, some of these, though, like in this question over here, f of n and g of n, f of n is a quadratic growth rate, g of n is n log n, f of n is bigger than g of n, so g of n equals O of n is correct. F of n equals omega g of n is also correct. Anything else, though, would have been incorrect. So, I don't know. I mean, to me, I don't. But anyway, that's kind of, I guess I won't cover every one of these, but that's sort of the idea. So I don't think the functions themselves were too complicated. These ones were the same. Because remember, 1.5 up to the power n is exponential, which is much faster than n to the 100 or 95. So that plus n to the 100 makes no difference because exponential function is definitely be bigger, so it has a bigger growth rate. So it's 1.5 to the n. Same for g of n. And this one here, f of n was, g of n has a larger growth rate than f of n. This one, so I don't know. So that was that, I guess. So it's on to the next ones here. I think I'm gonna go over maybe the reordering functions one. So the rest of these I won't cover. I'll probably cover maybe the last few as well. Just maybe the last two word problems. So reorder functions. Let's look at this one. Okay, so let's look at the first one. So here we have natural log of n factorial, which remember it's n log n. I've shown this many times in this semester in class that it's going to be n log n. You can use the integral of natural log, which is n log n minus n, it's n log n. It's going to be quadratic. So basically, the smallest one is going to be n. This one, the smallest one is natural log of n factorial, the smallest. The next biggest one is going to be, well, n is 1.5, because this is n root n, which is bigger than n log n. This one here is quadratic, that comes next. And then these two functions, the last one, which has 1.0001 to the power n plus n to the 500 and n to the 501. So n to the 501 is bigger than n to the 500, but this this function, 1.00001 to the power n, is exponential growth rate, which means that that's going to be bigger than all of these. It's exponential. So it doesn't matter how small this base is. If let's say if it's bigger than 1, it's going to be bigger than any other polynomial time algorithm. So n to the 501 is polynomial. Even though it's a very big exponent, it's still a polynomial. This one is exponential. This one's going to be the largest of all of them. So it's going to be first ln and factorial the smallest, then 33n to 1.5, then 33n squared, then n up to 501, and then this final exponential one over there. On this question, let's see. So we have 7 to the power 10. That's a constant. So no matter how big the constant is, it's a constant. It's not a growing value. So any constant always will come first. So that's going to be the smallest one, 7 to the power 10. And then we have these two functions right here, which these are both going to be just n root n. Because n log n plus 15n root n, well, n root n is going to be the bigger, the more dominant term. And over here, if I take square root of n cubed, it's going to be n up to 1.5, which is bigger than n log n. So these two functions right here, they both have the same growth rate, n root n. Growth rates are equal to each other. The smallest one's going to be 7 to the power 10, and then 2 to the power n, and then 3 to the power n. And using L'Hopital's rule, we can very easily show that these two functions, 2 to the n and 3 to the n, are not the same asymptotically. 3 to the power n will be bigger than 2 to the power n. So I won't cover all of these, but I guess if you have any questions as to why you lost points on these, of course, you let me know. Either email, Discord, office hours, whatever you have to do to ask me. But that was, so I pretty much what I did, I was trying to be kind of nice about grading on these ones. So if you missed like one, it was like 2 points off. If you missed maybe more than, if you had like, it would be like sort of 3 points off if you had some other problems. If it was really a giant mess, I took off 5 points. If it was like a mess, which happened on some of them where it was like all over the place, where it was like this is as wrong as it gets basically. That took off only 5 points just to not be too harsh on this one. So um, that's that. So let's go ahead and look at the this binary tree code. I had all kinds of really bizarre answers in this one, where it was like checking if it has a leaf. It's like, I mean, I looked at that and thought, well, I mean, every binary tree has a leaf, so it's okay. Or they looked and said, well, if root has no children, okay, but so I initially passed the root into this function, yes, because every binary tree function code, you always pass in the root initially. I put that there just because I'll get questions during the exam and say, oh, wait, you passed the root into this function? And it's like, yes, of course, you always pass root into this function. I've been doing that for every example so far. Why would I suddenly now just not do that? So I put that there just to make it clear that initially, when I first call a function, initially I'll pass the root of a binary tree initially to the function, but as you can see, R is going to traverse this binary tree. So what's happening here is this function returns true if the tree is a glorified linked list. It returns false otherwise. So if it has two children, then it would be false or false, and then it would not sort of run this if statement, but it would just jump to the else and return false. If one of these two is a null, then it's going to go ahead and recursively go further. And if both sides of the tree are either null or only has one child, it's going to keep on continuing. At some point, if we hit a leaf at some point, then that means we had no cases where there was any two children. So basically, if a two-child node exists, it returns false immediately. So it returns true if it can't find any two-child sort of nodes. So that means if it's sort of a linked list looking binary tree. So also I did say during the exam review, do not just, like sort of, write that, okay, if R equals null returns true, if R left equals null or this, and I said in class, don't like sort of paraphrase the entire code. And of course, people did that. And I was like, well, I said that in class in person and online. It was also recorded, not do that. And people still did that. So, no. I mean, this one could have been a little bit, this one might have been a little bit of a harder question, so I'm not going to be really too, it was definitely not so simple, I guess, is probably the right word. So, I mean, that's okay. This one was kind of okay to miss this one because it wasn't so easy. So the free response question is towards the end. Okay, so the first question really threw people off because they thought I was talking about the whole list being sorted. So the list that was given into the function is actually sorted, which is not what I meant because when we do insertion sort, remember, you trace out and for homework assignments. So as I increments, you have that sorted sublist within your list as you're going, right? That's how insertion sort works. So suppose that the element that comes right after that sorted list, that key element, if it always happens to be the middle element of that potentially sorted sublist, what's runtime going to be? Well, it's going to take n over two steps, or in this case, I over two steps every single time. I goes from 0 to n minus 1. So it's going to be quadratic, but it's going to be quadratic divided by 2, but it's going to be still asymptotically a quadratic growth rate because every iteration of the inner loop is going to have some linear runtime. It may not be all the way down to 0, but it's going to be, linear divided by 2 sort of runtime every single time. So it's going to be n squared still. So that one might have been a little bit of a tougher question. So that's this one's okay to have missed because this one was kind of one where I try to ask a question or two where okay, it's not super straightforward, but anyway. And this question over here, so to run insertion sort. So let's say half the time the inner loop runs 0 times, and half the time it's going to run the worst case scenario. What's runtime going to be in that case? Well, it's going to be quadratic because n squared because okay, so n over 2 times is going to run 0 times plus n over 2 times it'll run linear time in the middle for inner loop. So it's going to be essentially that O of n plus O of n squared, so O of n squared. Because that half the time where it does that is going to kind of surpass, because it's going to be quadratic right there in that half the time issue. Because it runs n over 2 times constantly, so every other time is going to be the worst case, which will still be quadratic if you count the number of steps. So anyway, that was that one. And this question here, this question right there was a little bit of a, so essentially f of n equals O of g of n. So if that's the case, this is always correct. And the answer here is that, well, this ratio could be 0 or larger, not just larger than 0, because f of n doesn't have to be equal to g of n. G of n could be larger or equal to f of n. So this L'Hopital's rule ratio could be 0, or it could be a constant. It could be either. So it doesn't have to always be just larger than 0 is the answer. But it can't be infinity though, because that would violate the initial statement there. So I guess the real issue also with this exam was that it was an online exam. And the thing is that if let's say we had a class in person, I could have had questions like, trace out quicksort, trace out merge sort, trace out search and sort. I could have done something like that. But the problem is that, well, on an online exam, it becomes a little bit challenging. And also it's online, so I have to also make sure that, yeah, I mean, I guess the issue is that you have notes as well, so I have to kind of make it where notes can help you, but you can't just look at your notes only and just do a pattern match and that was it. So that's kind of the issue with this. So the final exam will be a little bit easier, I believe, because it'll be mostly, so we'll have like several algorithms covered in class and just trace it out as done in class. It'll be just like that for the most part. So a big chunk of the exam will be essentially out of those kind of questions. I'll have some true or false and some explanation-based questions here and there, but it'll be mostly straightforward like that. So I guess, yeah, because maybe in general, I think it's kind of a pattern in my classes in general. So always a midterm always kind of goes a little bit rough, and the final usually goes better. It's kind of become the pattern, I guess, over the last couple of years of teaching CS302. So I guess that's just how it is. Maybe first exam because it has a lot of weird math stuff going on, which is kind of a little bit confusing at times. But the final will be easier. I mean, it's going to be more straightforward questions, I would imagine. So, as for credit assignment, we'll see. So it's just it's based on the timing and sort of the business for the semester right now. For me, it's sort of might be a little bit challenging to create an extra assignment for extra credit, I guess, like that. But I'll try to like do some type of like, rescaling the grades at the end and try and apply some kind of a bell curve towards the end and so forth like that. So I'm trying to make it so the assignments are definitely worth more than the exams, and I think the final will be easier, more straightforward. So that's going to be sort of the benefit right there will be that. So um, yes, that's sort of situation right now, I guess. So anyway, if you have any questions on the exam, of course, you can send me a Discord message. You can also go to office hours to ask for questions there. So I'll be available for any help on that if you have any questions. But I guess I can't spend too much time talking about this. I want to go into hash maps soon. Any way to show when using Valgrind? I mean, I'm mostly Valgrind just for memory leaks. So if Valgrind gives a bunch of weird errors, you can probably can ignore that because often Valgrind will go ahead and tell you, oh, you have a dangling pointer hasn't been set to null, but usually if you don't reference a dangling pointer, it's not going to be a problem. So um, I don't know Valgrind. I'm not really sure how to use Valgrind in every single way. I mostly just know how to use it for memory leaks at the end. So I'm not even sure if it really knows how to tell you exactly which line caused the leak. It just tells you, yeah, there are memory leaks in your program. So you have to use a debugger probably to actually check for that. It does sometimes give you issues. I think there's like you use you use some type of a Valgrind flag maybe to check for more errors. I just don't really know too much of Valgrind. Most use it just for memory leaks, and that's about it really. So I think there are sort of flags you can use. You can probably look that up. The Valgrind dash and some flags you can use, which will basically just give you more errors, which give you more potential problems. I think it would check for, yeah, mostly for dangling pointers and so forth. I don't think it tells you what line ever, where an issue might have happened or what line would have been in leak. I don't think. I'm not sure if it does that much, but yeah. So, um, all right. So I guess for now that'll be just the exam sort of kind of going over the answers. But of course, let me know if you have any issues or questions on the exam, and I'll definitely explain everything to you if you have any problems, if you don't understand why this was wrong, and so forth. So anyway, yes, now I'm going to sort of go over what's the wrong uh, or hashing, I guess now is the next sort of topic in this class. So we're definitely going to want to spend some time talking about hashing for sure. So anyway, last time I went over, let's see, what did I get last time? So hashing over here, and I didn't get that far. So okay, so I think I got a little further in my afternoon class. So, okay, so we have our hash map. And basically, just to recap, this is from a while ago because this was from, I think, last week, Monday, because we had the exam on Wednesday. So it's been a while. So I'll refresh a few of these contents here. So it's going to be a search structure, and it's definitely going to be faster, or in average cases, much better than AVL trees, except that it'll waste more memory to make this work, but it's going to be faster than an AVL tree. So the idea is the hash function is going to be used as our searching mechanism. So basically, every single item in our hash table contains a key value pair. So we're searching for a key, and we're going to retrieve a value field for that key. That's basically how hash map works. And hash function is going to be our search, basically. And the idea is we're going to have, so internally inside of a hash object, we have a very big array of all of our elements. And we want to have this array be very much not full, very empty, because the idea is that, see, down here, a collision can happen. So essentially what happens is that the hash function, we pass in the key and return some index in the table that this key will be mapped to, or the key will be saved to. Now the problem is that there are moments where you can have two separate keys and a map to the same index in your hash table. When that happens, you have a collision, and a collision is going to cause the runtime to get slower because that's not really ideal to have a collision. Now, if you have a few collisions, that's okay, but too many collisions, though, is going to cause the runtime to slow down. So the idea is that a good hash function will fix this problem, and a very large table will also fix the problem. So, I mean, it is not going to automatically guarantee to fix a problem, but a big table will make it very unlikely to have a collision. So, for example, if I have, let's say, a 1,000 element table, and so far only 5 elements actually contains a key and value, and the rest are empty, then the probability of having a collision is very low because we only use up only less than a percent has been used up, which means that's a very high, very good chance that if you insert something, the high probability it's going to go somewhere where it's empty, where there's no actual key in our table. So therefore, it's going to cause no collisions. So that's going to be sort of the idea for how we do hashing. So hash function has to be pretty good, but also a big table will make it so it's unlikely to have collisions. So I guess I want to first go over just a built-in type in C++, just to get an idea of how hashing works. And of course, then we'll go over the actual details of how, you know, how you would implement your own custom hash data structure. Let's go ahead and just go over this sort of type that's sort of in STL. C++, so it's a given type. So let's go ahead and talk about this. So I'm going to write a program to actually, will be given sort of an array of names, and I want to actually sort of condense that list is the idea. So anyway, I'm going to have my program right here. So I'm going to, of course, include IO stream, include unordered map. So this type right here, that's going to be your hash map basically. So it's actually given to you in C++. It's actually similar to a dictionary in Python, but in C++, unordered map is a type. Now I guess I'll include string as well, just in case, I suppose. String. And I'm going to have using namespace std. Of course, I'll have my int main right below. So I'm going to first have sort of a string or an array, string array of names. So I believe, oops, I should have included vector as well in my program. So I have to include that. Vector. And then I'm going to have their string. I'll have it be just names. I believe this approach will allocate this. So I'm going to have maybe just a bunch of names right now. So I'm going to have, let's say, Tom. Let's have Ted, Sue, Jim. I'll have Ted again, Sal, Tom. I'll have him be Ted once more, so a few times. So we have this array of strings, and I want to write a program that's going to condense this list, where I want to eliminate duplicates. So in this case, we have Ted 3 times, we have Tom twice, so we want to eliminate those duplicate names. So obviously, the very simple way we can do this, we can have a nested for loop that will go through and figure out if we've already seen Tom in the list once before and so forth. So it's a very simple way of doing this, but we want to improve this using a hash map. So we're going to have another vector over here, vector string. This is going to be, I'm going to call this maybe condensed. I guess that's the right way of spelling this. So condensed is going to be my new vector, which has all the names for my names vector, but it's going to have a condensed list. So we're not going to have Tom twice. We're not going to have Ted 3 times. It'll be, we're going to condense those names. But here's where we're going to have the important part. We're going to have this unordered map. I'm going to use string and bool. I'm going to call this maybe duplicates. So this is going to be our important type right here, unordered map. And this string, that's going to be the key type. And this is going to be the value type. So we're going to map a person's name to a true or false. So the whole idea of doing this is so that way we don't have to actually traverse the list to actually know if a name has been already seen before. We're going to mark them using this structure. So that's how we set up a hash map. You have to give it a type, the key type, and a value type associated with it. So we're going to map to a name, maps to a true or false. We can also go over an example, also we sort of do a simpler example as well. But I'll first talk about this one because this one's kind of a useful example involving hash maps. But anyway, we have this structure over here. So let's go ahead and try to I'm going to draw next to this right here, which is going to be sort of so inside a duplicate sort of array internally, it's going to actually have sort of this structure built into it. Just go ahead and try to draw this out. So inside, we're going to have this, so inside duplicates, so internally, in this object, duplicates, is going to be an array. It's going to be our hash table. So I'm going to do a very high-level view of how this actually would work. So I'm going to first do the following. Well, I'm going to write a loop. So for int I equals 0, I less than names dot size. I'm going to traverse through this vector. I'm going to put a bracket here and then if not duplicates names I, going to add it to my condensed vector. So I'll go ahead and I'll trace this out once I have the code written out. There's not much left to write here. Then I'll do this. It's kind of familiar. It's almost like I've done this example before this class. I'm not sure I did this already. It seems like, I think maybe OneNote actually didn't save on my work or something. I'm not sure. This looks familiar. But anyway, I guess I can talk about it. I don't think I discussed this. I think I had a different example last time I was talking about. But it seems like OneNote didn't save it though. So I kind of forgot where I left off from last week. I believe I did sort of begin talking about this, I think. So just correct me if I'm wrong, I guess. But I'm pretty sure I covered this last week. But anyway, so in this case right here, we have the following sort of loop. Okay, so I did a different example. Okay, that's good. So I'm not sure why OneNote didn't save this. Okay, so I did sort of go in, I believe I started talking about this a little bit. I think I actually was going into this, but I don't know why OneNote didn't save that. Okay, so at least, well, same names. Wow. How about that? I was able to recreate that same example. Cool. Oh yeah, that was one where I actually used, oh, I think I used, so I think that was when I used sort of names to their ages I believe. So it was like I mapped the person's name to his or her age using it was a string int map. Yeah, that's what I used last week, but it wasn't saved on OneNote for some reason. Oh, duplicates, okay. All right then. So anyway, all the same. Wow, that's I don't know, that's weird because I didn't memorize. I just randomly put these names down. Okay, let's go ahead and just begin. So I guess I'll trace this example out. So I initially is going to be 0. So we're looking at this name Tom initially. So what happens is names I will be just, so it'll be Tom. So I first go to duplicates and I use the bracket operator. And I'm going to pass in essentially Tom into this brackets operator. So what happens is this bracket operator is going to look up and find where is Tom in my structure. So what happens is that that string, that key, Tom, is going to be passed into a hash function. The hash function will take in the name Tom and it'll do some type of computation and it will spit out some index. So Tom goes to index 5 or so in this table. So what'll happen is in this table, so I'll go ahead and I'll just put the brackets here, indices like this, just to help us out. So let's say Tom has index 4, let's say. So we go to index 4 in our table. I'll put K and V over here, just because. So the key in this index is empty, which means that Tom has not been inserted yet. So we're going to go ahead and insert Tom into this. And then the value will be false. So hash map actually also what it does is if you create a new entry for an element, it's going to automatically assign some default 0 value to the element. So for a Boolean, a default would be false. If our value type was integer, then it would be a 0. If our value type was a character, it will be a null character, and so forth. So it assigns some default value of that type. If the value type was a custom type, it would use the default constructor to assign a default value to the value field. So what happens is we didn't find Tom in our table, but we found a vacant spot, which means we go ahead and create the entry for Tom. Then return the value field, it contains false. So not false will become true. We're going to insert Tom into our condensed vector. So I guess put the condensed vector below over here so we have it. So we can, as reference, condensed, and so far Tom would be in this dense vector. Insert Tom in there. And then we're going to mark that you've seen Tom before. So you go ahead and use duplicates, names I. Names I again will be just Tom, as always. It's not as always, but we're still index I. This I is still 0, so we're looking at Tom still. We go to duplicates and look and search for Tom. So again, the hash function, we pass in Tom, it'll spit out 4 again. And Tom will be index 4. We see Tom right there, so we found Tom in our table. I want to assign the value from false to a true. So that marks it. So from now on, if I see Tom again, it'll have a true value, which means I know I've seen Tom before. So this is supposed to enhance the runtime because I'll go over in a second what's the enhancement really, but that's what we're trying to do. It's a very fast and simple way to verify if we've seen Tom before. Look up Tom in our table. If it contains true, that means we know we've seen Tom before. So we don't add it to our condensed list. Then I now becomes 1. So names I is now going to be Ted. So I'm going to go ahead in my if statement. I want to look up where is Ted in my table. Let's suppose that if I go ahead and look at Ted, so we had the bracket operator, we pass in our key. So the bracket will take in some key value. And for Ted as our key, it's going to return the hash function internally is going to find the location of Ted would have to be at index 7. How to do that? Well, the hash function just takes in the string Ted and does some computation. It happens to return 7. So index 7 is where Ted has to go. That's going to be Ted's designated area in our table. So 7 contains a blank, which means that we have not found Ted yet. Otherwise, Ted would already be here. So we're going to create the index for Ted. And the value would be false because we're going to use some default value we're going to use to assign to the value field for this element. So it contains false, so not false is true. It'll enter this if statement body, and it will push Ted into our condensed vector. That. Then we're going to look up Ted. So names I will again just be Ted still. We'll look up, we gotta find where is Ted in our table, the duplicates, and I'll pass in Ted. And once again, if I use the same name, Ted, the hash function will again compute 7. And the reason, and let's say the hash function had different value was computed this time, we wouldn't be able to find our existing record. So the hash function has to always return the same exact index for the same exact key. To look up TED again, the hash function will go through, will pass in TED, and it will again compute 7. Index 7, we found TED right there. We're going to assign it to the value true. So we're simply trying to find TED again. But every time I pass in TED into this operator bracket function, it's going to always return 7. It's always going to locate TED at index 7 every single time. So that's how we can always find existing elements. It has to return the same index back, or else we can't find existing elements in our table, and then this would be a very not so good structure then at that point. So now the next element in our array is going to be Sue. I'm going to go ahead and just kind of speed this up a little bit. So now names I will be Sue. So we have if and then not duplicates bracket, and we're going to pass in Sue because names I will be Sue in this case. I pass in Sue into this bracket operator, and it's going to find that Sue is going to be at index 2, let's say. We jump to index 2 in our table, and the key is blank, which means that Sue is not inserted in our table. So I'm going to go ahead and create the entry for Sue. Value will be false. It returns false because when I go ahead and say duplicates names I, it looks up the key value and returns the value for that respective key. So in this case, it looks up where is Sue. It found Sue. Well, it didn't find it. It created an entry for Sue, but creating entry is just as good as finding it because now we know where Sue is in our table. I return the value field, which is going to be false. So not false will be true. Enter if statement, and it will insert Sue into our condensed vector. And we're going to mark, we've already seen Sue. So we're going to go ahead and use this last line of code right there and say duplicates, pass in Sue. And again, passing in that Sue, that key Sue into this hash table, it's going to again compute the value 2 in that hash function. Every time I pass in Sue, for this particular instance, it's going to return 2 every single time. So note that Sue has to go to index 2. We jump to index 2, we see it. Sue is right there. Update the value to be true. My mistake, should have same color scheme. That. That denotes, so true denotes for us that if the key has a true associated, which means that we've already seen that name before. That's the whole key to this, or the whole trick to this, I suppose. So now I'm going to look at Jim next. And I'm going to pass Jim into my hash function this time. So we have our loop that will go through every name in our vector. We have duplicates, and I pass in Jim, because names I will be Jim in this case. So I go ahead and look at Jim. And let's suppose that for his hash function, Jim gives us the key value, or index, sorry, the index 9. So Jim happens to go to index 9, and index 9 in this green table is blank, which means that Jim has not been inserted yet into this structure. So I'm going to set this key to be Jim, and the value will be some default, which will be false in this case, because the default Boolean is going to be false. So I return that value field. I found the Jim. Now, Jim wasn't there before, but I created the entries, so that's just as good as finding it, I guess. So I found where Jim has to be. Return a value field associated with Jim, and I'm going to basically check it. So here it returns a false, so not false becomes true. So we're going to add Jim into our condensed list. That. And I'm going to mark that I've already seen Jim before. So I have to again look up where's Jim in my table. So I passed in again Jim. And this internally, inside the duplicates object, internally that hash function returns 9. Index 9 is where Jim has to go. We jump to index 9. We see there's Jim. I'm going to assign the value to be true. So on to the next name. Let's look at Ted next. So we already know we've already seen Ted before, but let's go ahead and go through this hash map process. So names I will be Ted in this case. So duplicates, I pass in Ted. I have to find where it's Ted in my table. So for the way we have it set up, our sort of hypothetical hash function, if I pass in TED, it returns 7 every single time. So every time I pass in TED, it returns 7 every single time. So it's going to find TED right there. And we found a match, we found TED, and the value will be true. So now it returns true, so not true is false. It will not enter its if statement body. Because if, let's say, a name has a true associated with it, that means we've already seen that name before. So don't add it into our table. So that's kind of the trick to this. Let's look at the next name over here, which will be Sal. So again, we try if non-duplicate, so pass in Sal this time into this bracket. And we check, let's say Sal happens to give us the index 5. We jump to index 5, we see that there's no key, there's empty entry. So we're going to go ahead and make the entry for Sal. The value will be false. So it returns false, so not false is true. We're going to insert Sal into my condensed vector. I'm going to mark Sal to be true because, again, we look up where is Sal, and it's going to return 5 again. So every time I pass in Sal into this bracket, it's going to always return 5 every single time. So index 5 is where Sal resides. I mark it as true. And then from now on, the rest of these names I have Tom and Ted left. What's going to happen is that, well, we're going to pass Tom into this duplicates bracket. So duplicates pass in Tom. And Tom has index 4 because in our hypothetical hash function, it has 4. So it jumps to index 4 and it sees that the key value will be Tom. So you found Tom, but the value is true. It returns that true value back. So not true becomes false. It's not going to insert Tom into my table. And same thing for Ted. You'll look up Ted. You'll find Ted index 7. It returns true, which means that you've already seen Ted. So not true will not run this if statement, essentially. So a simpler way of doing this actually would have been, instead of having this if statement over here, we could have had a for loop that would search through our condensed vector. Let's say I want to see if I want to insert Ted, I could traverse this vector and find Ted right there and not insert Ted into my condensed vector, right? But that would take O(n squared time. So I could have another loop right there which would traverse this condensed vector for duplicates. So if I go through this and I see a name or it's already here, then don't insert this. That's going to take, O(n). This, in fact, ideally is constant. So every hash table lookup, ideally, the runtime will be constant. So this is a very fast lookup. So instead of having to search through condensed, or I could insert elements into an AVL tree and search through that tree. If I find the entry in my tree, then don't insert into my condensed vector. If I don't find it, then insert that name into my AVL tree, right? But that would take log of n time to find if a duplicate already exists. So a hash table takes O(1) time, or ideally O(1) time to find something. So I can, in constant time, I can locate if I've already seen that name before. So we're sort of taking this brute force approach, and a hash map makes it much faster, is the idea. So basically, this bracket operator for the hash map or unordered map is our search structure. We pass in some key, it locates, so this green array is going to be some private member inside of my duplicates object. So it's going to be all internal. It stores this table internally, and a hash function will sort of take in this string, and it will take the string and map it to an index in the table within our hash object, essentially. So we kind of think of it as the brackets. We can sort of think of a hash table or hash object as really an array, except that instead of using integers as indices, we can use sort of strings as indices. But internally, it's going to map a string to an array index internally inside of this inside this object. So basically we have, so the regular array version of doing this, it would take n squared time to eliminate all duplicates. If you use an AVL tree, it would be n log n time to do this. The hash map takes O of n time. So, good question. So, in practice, a hash is always used for most applications. Now, for databases, possibly some type of a tree structure is probably going to be used instead because it's fast enough. You want to, you don't have too much space, but typically a hash map is more common. Also, for competitive coding problems or for lead code problems, if you ever have any kind of search going on, a hash map is the way to go. But a tree structure is mostly used sort of for databases for most part because database is already pretty big already as it is. You didn't want to have extra space like the extra useless space because you already have a lot of space for database already as it is. So it has to have a tree structure used over there for that. But for other problems though, a hash map is usually always the way to go, typically. Yeah. So the overall runtime is going to be O of n, but the if statement is going to be O of 1 because when doing a search, we're not going to actually traverse this array in a linear loop, linear sort of search fashion. We're going to have a hash function, which hash functions are supposed to be quick. So ideally, a hash function is supposed to be fast and not cause much collision. So that way, a hash function will very quickly determine where in this array does Sue, Tom, Sal, Ted, and Jim have to go. So this statement right here is going to be constant. We do this n times, so this overall will take O of n time. The lookup time will be O of 1 because the hash function will very quickly map exactly where you have to go instead of having to have to linear search through it. Or if it's a AVL tree was used over here, it would take log n steps to find the key. Over hash maps, it takes O of 1 time find the key. Well, ideally O of 1 time. So this will take O of n overall, but the if statement portion to find a duplicate will take O of 1. The hash function is very quick because if I want to see where is Tom in my table, I don't have to go through this table and look at index 0, 1, 2, 3. Oh, there's Tom, index 4. No, the hash function will just automatically map you to 4. The hash function will be some constant operation to quickly find where Tom has to go, essentially. So this is a very kind of a high level view of this. So for assignment 6, you'll use this unordered map, basically. Assignment 6 will be pretty easy, actually, because you can just use unordered map. And I want to first have an assignment like that because what happens is when I have students create their own custom hash map, here's what typically happens. They create their hash map, but then they have no idea how to actually use it in main. So this unordered map will give you an idea of how a hash map is used to solve some problem. So your own custom hash map you're going to create will work just like unordered map. Same idea, except it'll be called hash map instead. But also it's going to take the object and the bracket operator will be used to locate. So it's supposed to be bracket operator. I'm going to make sure I'm more straighter with these brackets. That. So it's going to use a bracket operator. You have to overload this for your custom type, basically. So that's going to be your assignment 6 is using unordered map to solve some problem. I promise it will not be anything really that hard. So it should be a very nice, easy way to kind of sort of, how should I say, get into hash maps. A very simple method of doing this. So anyway, but of course, I'll go over, I'll talk about the assignment as well to give you an idea of how it's going to work. But very similar, it's going to be just sort of using an unordered map type basically to solve some problem. So you're gonna have to maintain several datas, and you're gonna have to maintain it in a hash table. So you have to have a string for your key or map to some type of item. You have to look up that name several times. You can look it up using your hash table instead of linear searching through a different array. So anyway, um, I guess now I'm going to go over the actual implementation details as to how to store, how to maintain a hash structure. So let's go ahead and I'm going to go into this board, which is going to be separate chaining. So we're not going to spend really any time going over what's a good hash function or a bad hash function. We're going to go over how to really maintain a hash function or hash table structure. So separate chaining is going to be one way to handle this. Now, conceptually, this way is the easiest. Not easier to code because this involves actually, let me put this right here just to make you feel comfortable. It's going to be an array of linked lists. I know how much you guys like, linked lists. Having an array of linked lists definitely makes the problem even worse. But conceptually, though, it's actually the easiest to maintain. So what we do is, so what's going to happen is when a collision occurs, um, we link the node into a linked list. So for each element, there's going to be an array of linked lists. So every linked list is going to maintain all the keys that essentially collided with one another. So all the collisions are maintained in that sort of array, in that linked list, essentially. So I'm going to go over how to actually create, or how to set up, how to create our own custom sort of hash map. And I'm going to sort of trace out how to maintain it using a separate chaining. So we have really two main methods, separate chaining and we have open addressing. Open addressing has several parts to it. Those are two main sort of common ways to maintain a hash table. So if you want to have your custom hash map, you're going to have a template first. So it's a templated class, of course. T1, comma, type name, T2. So T1 is going to be a type of your key, and T2 will be a type of your value field, the two template class. I'm going to go over every single aspect here, but I'll go over the real important ones. So of course, we have our constructor and all the other good stuff, but I'm going to go straight to the actual important members here. We're going to have the following. So that's going to be, this function is going to be the hardest function to write for hash structure. It's going to be your search function. You're going to pass in some key, and then we'll look up where is that key going to be in our hash table. When it finds it, it returns the value field by reference. And the reason why is because that way we can actually update the key value somewhere outside the scope of this class. So I'll definitely go over exactly what I mean by that as we do an example involving hash maps. So what's going to happen now, I think there's no other important member. There are other members, of course, but I'm going to sort of leave that part out for right now because those are not really, I want to focus mostly on the real important parts, essentially. So we're going to have, basically, in this case, we're going to have a struct. I guess I'm going to call this maybe table item T1 key to value. And since this is going to essentially be sort of a chaining method, we're going to have this also included. But this is actually more specific, really, to the following. So for separate chaining, we have to put this here. But in reality, that T1 key and T2 value are real important. That's what makes this into a hash sort of structure. That table item star link, that's mostly because we're going to have a linked list. They'll link all of the keys together in each element of our table. And then we're going to have essentially now a hash function. And I'll call this, I'm going to call it just string. I guess I'll call it string K. So now, of course, this hash function, you could, of course, template it, but I'm going to make it specific to strings. But of course, you could overload this hash function for different key types. But for now, I'm going to just keep it sort of simple. So we're going to have it where it'll be sort of specific to strings. But of course, if I want to have a hash function where the key is integer, then say int hash function int k. So you can have more hash functions for different types. So anyway, this one will have a string type. So for this particular hash function, very simple hash function we're going to use. We're going to basically just have it just say return to lower k index 0 minus a, and then mod it by table size. I'll put the table size above right here. So actually, I'll put it below. We're going to have an int items field and an int table size field. We have these two fields also maintained in our hash structure. Table size will be the size of our table, and items is going to essentially be how many elements we stored in our hash table so far. That's what this is really going to actually do. So we typically want to maintain how many items we have so far because we want to know how full our table is. So we typically have to take a ratio of items over table size. Put this here in red. Load factor is always going to be the items over table size. Load factor is also sometimes known as alpha. They use alpha sometimes for this. But essentially, we want to know how full our table is. If it's very full, then we have to, possibly resize our structure to make sure that, because we don't want to have our table to be too full, because then there's a very high probability of having collisions in the future. So if this happens, if it's too high load factor, we have to resize our table to make more space so that we lower the probability of having collisions going forward as we insert elements into our table. So what's going to happen is this hash function will be used in our bracket operator. Let me go ahead and actually write out this function right below. So I think I'll close this up. So it doesn't have everything in this hash function, but I'm mostly focusing on the important parts here in this class hash map. So for our bracket operator, is actually not real. I think it would actually involve maybe, okay, fine, T2, hash map, operator, bracket, then T2, I think it has a template above it as well, but we'll focus just on this. So here's how this bracket operator is going to work. We're going to first have an index, so int index variable within this function equals hash function key. So what happens is that, well, it's going to basically look up where is the key going to be in our table. So our hash function we have is pretty simple. We take the first letter of the string, minus it by a, mod it by table size. Now, modding by table size is important because otherwise it can go beyond the bounds. It can go beyond our table bounds, and we don't want that. So we have this mod to make sure that we don't go beyond our table size, basically. So we'll do an example of how this works, then we'll see what's going on. But that's the purpose of this. So it's a very simple hash function, just so it's easy for us to conceptually understand what's going on. So it's going to give us an index. And actually, in this scenario here, I made a mistake here. We're going to actually have the following structure. So I have to add this in between these two. It's my mistake for not putting this here earlier. So table item star star table. This is going to be our hash table, basically. And because it's an array of linked lists, we have to have a two-star sort of pointer because it's going to be an array of linked lists, basically. So for a non-linked list type, it'll be just 1 star. But for now, it's a linked list. We're using an array of linked lists. So you have to use this approach. So our constructor, of course, in the constructor, it would just say table equals new table item star. So I'll just put this here just because. So in the constructor, so in default constructor, you would just have essentially table equals new table item star, and then whatever you have for your table size. The table size, you're going to set that as some value in your constructor, and you're going to use that to set this table, this array, essentially. It's going to be an array of linked lists. So it has to use table item star because of that, because it's an array of linked lists. So, but we're not going to go into implementation details too much. I'm probably going to try to, I'll probably go over details more in detail when we have maybe in our assignment 7, which is going to be definitely the most fun assignment of all. Is always a hash map one is what always gets people, but I'll do a lot of examples on hash map for next, few sessions. I'll try to go in detail when we go implementation for assignment 7. But anyway, this will be our array. The way it works is we're going to look up, so we're going to look at table at this index. There's actually not really C++ code. I'm going to look this up. So I'll write this over here. Maybe in red. I'll write it in red. So it's not C++ code. I'm going to look up table at this index. And then we're going to try to see. So look for key in table index linked list. If we find it, return the value field. Return value field of the node, else create a new node. And of course, and then return the value field. So I'm going to actually do a more of a sort of visual representation of how this would work, because it might be a little bit complicated by looking at just the code and the pseudocode here. So let's go ahead. I'm going to kind of paraphrase how the code would work in this example. Let's go ahead and just for right now, let's create an example. Maybe then it might make sense how the code will all kind of come together. Okay. So I'm going to have, I'm going to have a hash map. I'll use a string for my key type, and int for the value type. And I'll call this people. And essentially, let's go ahead. I'm going to zoom out so we can write some notes next to this. We're going to have the following structure. This is going to be that table field within this people object. And let's suppose for right now, let's suppose that the table size is set to 10 and the items is set to 0 initially. So in our constructor we're going to have created, we're going to basically just set table size to 10, items to 0. So therefore, here's our table. Like that. Takes a long time to draw the brackets out, but that's okay. So here's what's going to happen. Here's what we have internally. Inside this people object, we have this table, and each of these will be a linked list. And this right here reminds me of in Sonic 2, we have to play in that water level, and the final boss, Robotnik, has these two kind of poles, and then arrows kind of shoot out. You have to jump on top of the arrow and hit them. It reminds me of that part in that game. Anyway, so this will be an array of linked lists. The table 0, table 1, table 2 are all individual linked lists. Okay, let's go ahead and do the following. Let's go ahead and first say people, and I'm just going to use, guess I'm going to use Bob equals, let's say 13. So for unordered maps, what's going to happen here is going to just, look up where Bob is in our table and assign 13 to it magically. Let's go ahead and do it our way. So our hash function, remember what our hash function was. So I could probably look up quickly right here. It just take the first letter, minus it by A, multiplied by table size. Okay. So Bob minus it by A will give us the value 1. So I have this list right here in front of me. So basically, we have this hash values here. So B minus A will give us the value 1. Modded by 10 will give us 1. So Bob has to go to index 1 in my table because to the first letter, Bob. First letter was B, lowercased it, minus it by A, that gives me the value 1. Modded by table size, modded by 10 will give me 1. So Bob is at index 1. Go to index 1, we have an empty linked list over here. So we're going to create the entry for Bob right here. So we just allocate a spot. I don't know why I did all of that. And then the key is going to be Bob. And the value is going to be 0. So what happens is index 1 was nothing there. So we basically had to just create the entry at index 1. And we create the entry and assigned this string that we passed into a bracket operator. We assign that string to the key field. And then the value is going to be some default of that type, which is simple to do. I'll go over the actual coding aspect of it later, but it's simple to set the default to. You have to just essentially assign it to be just T2 like that as a default value for that value type. And then we return this value by reference. So it's essentially created the entry for Bob, and we return the value field associated with Bob. Returns this V field and assigns 13 to Bob. Let's do maybe like one more since I don't have too much time left, but I'll continue this for sure next time. We're gonna say people. I'll just try say I can't think of a name right. I'm gonna try Dan. equals 10. So essentially, we're passing in Dan into our bracket operator function. So we go up to the code here for a second. T2 key is going to be Dan right now. We're passing Dan into this function. We gotta find Dan in our table. So we take this key, Dan, and first pass into our hash function. The hash function, I pass in Dan to the hash function. Hash function will just sort of take the first letter D, minus it by A, to give me the value 3. Then 3 multiplied by 10 will be 3. Index 3 in my table, well, it contains blank. Nothing's there. So I have to go ahead and create the entry for Dan. So I'll allocate the space. And I'm going to assign this to be Dan for the key. You have to insert whatever key we use, you have to insert that into the key field of that node. Because remember, every single element is going to be this table item type. Each node will be of this type right there. So create this entry, Dan, and the value is going to be blank, or going to be 0. We're going to assign 0 by default into it. And when we found Dan, return the value field of Dan by reference. So that way, when I'm inside of main over here, I can assign 10 to that value field because I returned it by reference. That will allow me to assign 10 outside of the class scope. So then it's going to assign 10 to the value field. We'll do some more examples of this next time. I'll also cover more hashing as we move along for the next couple of lectures. But for now, it's going to be it for today since we're almost actually past time now. So I guess take care, you guys. Stay safe. Thanks for watching. And I will see you guys on Wednesday.